Much for the kind introduction, and I would like to also first thank the organizers for the invitation and organizing this very exciting conference that I've learned a lot during the past 2 days. So I would like to start by acknowledging the people who have contributed to this work. So Li Fu and Rendong are the key drivers in my group working on correlated electrons in these 2D materials, and we have a really productive collaboration with Mohammed's group. And actually, the second part of our talk, I will show a series of work done, actually spearheaded by people from Mohammed's group, looking at the exciton and the electrons in TMD Mori systems. And we got our HBN from the NIMS in Japan, and we also have a good collaboration with Brookhaven National Lab to help us with the sample fabrication. And I would like to also acknowledge Ming Xie and Ilya Esterlis, who can help us with some theoretical understandings of what I'm going to show today. And of course, those are the funding agencies for this work. Okay, so Vinod and Jit, they have really done a wonderful job introducing the material system I'm going to discuss today, which is 2D transition metal dichalcogenide. So I'm not going to go too much into the details, but just to reiterate one point that Jit mentioned is that these 2D materials are actually an excellent platform to study correlated physics. On the one hand, we have a reduced dimensionality leads to weak screening and strong Coulomb potential. On the other hand, the effective mass of these carriers inside these TMD materials, they are actually pretty large. So naturally, you get a system with a large potential energy and kinetic energy. So for the past decade, we already know that these materials feature very large exciton binding energy. Exciton are very tightly bound, and they have large oscillator strengths. And we also came to realize that they can feature strong correlation due to these two effects, just for exactly the same reason. So in today's talk, I'm going to discuss some of our work of using excitons to probe interesting correlated states matter and perhaps engineer correlated states matter. And this is, of course, in a very larger field pioneered by many different groups, such as Kim-Fai, Attach, Feng Wang's group, and Xiaodong Xu's group. So on the one hand, because we have these excitons that are optically active, if there's any correlated electronic phase, you can use these excitons as a probe to probe whether you have a correlated insulator or whether there is any magnetism, and recently if there's any quantum anomalous Hall effect. So you can use it as a reporter for what's going on inside the 2D layers. On the other hand, the excitons themselves can also have interesting physics, right? So if I create a high density of excitons because of their bosonic natures, it is predicted that they can have this exciton condensate phase at actually relatively high temperature. In addition, if you put this exciton into a Mori system, you can create a bosonic Hubbard model. For example, there are predictions of realizing topological states using excitons in such systems. Okay, so I'm going to follow this slide and talk about our work of using excitons both as a probe and the effort of using excitons to realize some interesting phases of matter. So I'll talk first about in Mori free system. So just without any Mori system in monolayers or decoupled bilayers, we can already study some interesting electron-electron correlation and electron-hole correlation. Then I will move on to adding the Mori potential into the system and talk about their correlated electrons and excitonic behaviors. And eventually I'll talk about how do we potentially get rid of the Mori system but impose synthetic lattice potential using optical. So can we create an optical lattice for excitons and explore similar physics? Okay, so I'll start by looking at the electron-electron correlation and electron-hole correlation in a Mori-free system. So one of the prototype correlated state of matter is the Wigner crystal. Right? So if you recall, when the potential energy dominates over the kinetic energy, the electron would naturally repel each other and form this regular lattice, first predicted by Wigner back in the 1930s. So if we look at the scaling of the potential energy and the kinetic energy, we realize that this Wigner crystal is most stable at a low density where the interparticle distance r is very large, right? So that's when the kinetic energy is small, so the potential energy dominates over it. This typically happens at very low density and very low temperatures. Historically, the Wigner crystal has been very difficult to realize because the kinetic energy always dominates at densities comparable to the defect density. Typically people rely on applying a magnetic field to quench the kinetic energy. Back in 2021, a group of researchers from Tashi's group and also myself when I was a postdoc with Hong Kong Park, we realized that you can actually also realize Wigner crystals in this 2D semiconductor, in particular 2D MOSE2, exactly because of the reason I described before. You have large potential and a small kinetic energy. So we do so by using an optical method that I will describe a little bit more in detail later. And very recently, it's actually really nice to see that people can also use STM to directly visualize the Wigner crystal. This is from Mike Cromie and Feng Wang's group shown over here at the UC Berkeley. So they can directly see these more or less regular lattice structures. So over the past few years, what my group has been trying to do is to extend the material system where we can realize Wigner crystals. Previously, it was all realized in MOSE2. So we want to see if other materials such as tungsten diselenide can also host the Wigner crystal. The motivation is that here we can have different effective mass, different spin-orbit coupling, so we can study how these influence the formation of Wigner crystal. And eventually, perhaps we can combine Wigner crystal in tungsten diselenide with the one in moly diselenide and look at their interactions, whether you can stable other phases. So we create a structure where we have a tungsten diselenide encapsulated in 2 layers of HBN, and then we have a dual gate to control their doping level. To probe the formation of Wigner crystal, we use this technique developed by Tashi's group. So this very intriguing idea of using the diffraction of the exciton by this Wigner crystal. So let's say that I have an exciton that in a free space, you have a naturally hyperbolic dispersion. But when you put it into a periodic potential imposed by this Wigner crystal, now suddenly you have this proactive band folding, and this creates a higher energy state that's called the Wurm-Clamp scattering at the zero momentum state. So this can be probed by looking at the absorption of my excitons. So I would see 2 peaks, one coming from the bare exciton and another one coming from the Wurm-Clamp scattering. What's nice about this is that I can just change the density of the electron in the system and change the interparticle distance, change the size of the Brevard zone. So if I do that, I can see that I'll apply a voltage and change the density. As I increase the density, there is this repulsive polaron branch which dominates your spectrum response, and also 2 additional attractive polaron coming from the spin singlet and the spin triplet exciton binding to some charges. However, in addition to these main features, what you can find is that there is additional peak that's showing up over here that's corresponding to the Wurm-Clamp scattering. So as I increase the density, the interparticle distance becomes smaller, the pi over r becomes larger, so the scattering process, the energy difference between them become larger and larger, so we see a larger separation between the Wurm-Clamp and the repulsive polaron. So this was very similar to what Tachi observed in monolayer MOSE2. And if you squint a little bit, what we can see is that not only for the repulsive polaron branch or the exciton branch, we also observe the Wurm-Clamp features for these attractive polaron branches. So from this, we can potentially measure the effective mass of the repulsive polaron versus attractive polaron. So this is still something that we are trying to work on. All right. Yes. Yeah.
Splitting of the attractive polaron resonances seem to be substantially larger.
Between these.
Yeah, I mean, compare.
Yeah.
So.
Yeah. So. Yeah. So at first we thought it's due to the effective mass although we don't have a fully theoretical understanding of how the effective mass changes for the attractive polaron and the repulsive polaron, because that affects the slope of it. So we find that this Umkamp feature is actually very close to bare exciton mass, very close pretty well with the DFT calculation. This one somehow shows a smaller mass. Yeah. Yes.
This is a basic question. Experimentally, how do we know that it's Umkamp scattering? The other signal is from Umkamp scattering.
Yeah. So these features are very strong, right? So you can see them at all different temperatures. You can see them across all kinds of samples. This Umkamp feature only shows up at a low temperature, at a low density, and also only in some materials, like in some samples, which is very clean. So it doesn't show up in all materials.
But I guess my question is, how do we know there's Umkamp scattering being involved here? How do we know that there is Umkamp scattering happening here from the optical signal?
Oh, so so you see that there is a very faint feature. So maybe I should change the contrast. There is a linear feature over here, and this bright feature is corresponding to normal exciton, and this like there is a line over here corresponding to the Umkamp scattering.
Okay, thank you.
Yeah.
So if there's any variation in the Wigner crystal period from site to site, area to area, you'll probably see this broadening in the signal. Do you have any estimate of how narrow the original peak is and how much broadened it is just because you're looking at a large area?
Yeah, so that's an excellent question. So it turns out that even for this neutral exciton, we already have broadening due to both inhomogeneous broadening and also just natural broadening from the radiative lifetime. So in principle, we can look at the line width of this repulsive polaron, and we actually look at it. You have to be a little bit careful of how do you extract the line width, because it's a very small feature. So we developed some technique, actually shown in the previous paper. We need to do very careful fitting to extract that line width. So indeed, actually, there could be some variation across different spots. Of course, we are only probe diffraction limited spots, so we cannot probe. Actually, the domain sizes of Wigner crystal is typically smaller than your diffraction limit. Yeah. Okay. So another thing we can do is to look at the dielectric response of the Wigner crystal. So instead of just using the exciton in this same layer as a probe, what we can do is to put another layer in here, in this case MOSC2, and use the exciton in a different layer to sense the Wigner crystal, right? So as we might expect, if you have a Wigner crystal versus electron liquid, the screening of this layer will have different effect on the exciton energy in this MOSC2 layer. So this was a technique developed by Kim Fai's group, so-called Rydberg sensing. You want to use the Rydberg states of the exciton because they have large Bohr radius, so you can penetrate deeper or further from your sensing layer. Okay. So we do this type of experiments where we vary the density in tungsten diselenide, we vary the hole density, we'll keep MOSC2 layer intrinsic. So there's no charge variation in this MOSC2 layer. So initially we see that there is this Rydberg states. We can see very clearly 1s, 2s, up to 4s state of the exciton states. And as we vary the doping level in the tungsten diselenide, you can see that the repulsive polaron and the attractive polaron formation. The 2s exciton of MOSC2 actually shows some quite interesting behavior. So we know that over this range, in the middle, we are in the Wigner crystal phase. So the exciton, this is the 2s exciton. 2 exciton have some energy. But when you go to the electron liquid phase, there is suddenly a redshift of the exciton energy. So this is because when you go to the electron liquid phase, there is more screening of your Coulomb attraction. So the binding energy of this electron hole reduced a little bit. So because the 1s exciton, which I didn't show, doesn't change, so this redshift corresponding a slight reduction in the binding energy of the exciton. And what's quite interesting is that there is actually a sudden jump at the so-called quantum phase transitions where between the regular crystal and liquid phase. So how do we exactly understand the dielectric function of these regular crystals? We still don't know. We are still trying to understand. We don't fully understand, but this qualitatively this makes sense. Okay, I talk about how you can use an optical method to sense the formation of regular crystals. You can actually also use method to destroy it, to actually modify the electronic states. So one thing that we can do is to, in addition to this white light where we probe this Ohm-Clamp scattering, we can add another pump laser where it's above the exciton resonance but below the band gap, so that I create exciton population in addition to this electron population. If I do that and try to increase the pumping power, okay. So I see that with increasing pumping power, this repulsive polaron, this main feature doesn't really change, but the Ohm-Clamp feature becomes much weaker. And eventually, it disappears. Okay. Yes?
What temperature are these measurements at?
Yeah, sorry about that. So all of the measurements I will show is done at 4 Kelvin. Yeah, okay. So because we are exciting below the band gap, we are not creating free carriers directly. You can also see that there is no shift in the repulsive polaron branch. Of course, we are also generating heating, but by looking at the position of this repulsive polaron, we find that this disappearance of Ohm-Clamp is not entirely due to heating. There is actually additional screening effect. So very interestingly, in this tungsten diselenide, it's quite different from MOSC2. They are known to have dark excitons, so you can create high density of excitons without a lot of pumping power. So one experiment that we are trying to do is to compare these results with what's going on with moly diselenide, because in there you would have much lower exciton density, and then you can see whether the exciton population is really playing a role over here. Okay. So this is in the monolayer case. What we can also do is to actually look at slightly more complicated sample structure where I put 2 layers together and insert a thin layer of HBN in between them. And here, instead of looking at electron-electron correlation, I want to look at the electron-hole correlation. So what you can do is to, in this dual gauge structure, apply a voltage and separate the electron hole into 2 opposite layers, creating this interlayer exciton that was first observed by Attach's group in the similar device. When you do so, well, so here I'm showing the photoluminescence of the sample as I vary the electric field. You see that there is a nice stark shift because this one has a permanent dipole for the interlayer exciton, but the intralayer exciton does not show any stark shift because of the 0 dipole moment out of plane. What's pretty nice about this system is that you can see that the interlayer exciton photoluminescence intensity is actually quite comparable to the neutral exciton. So we can get very bright interlayer emission from such systems. This was pretty challenging to do before our experiments. What this could allow us to do is to explore this exciton condensate region. Because interlayer exciton feature separated the electron and holes, they have very long lifetime on the order of nanosecond to even microsecond. So potentially we can create high density of excitons. And we also measure the binding energy of this exciton, interlayer exciton, and found it to be pretty high. It's around 80 milli-electron volt, even though you separated these 2 layers. So this allows us to estimate the maximum condensate temperature to be around 93 Kelvin. So potentially we can create very high density of interlayer exciton and explore this region. Yeah.
How did you measure the binding energy?
Yeah, so that's an excellent question. So here I can measure the exciton energy at the 0 field by extrapolating to the 0 field. So this tells me the interlayer exciton. And I can also measure the band gap from the Rydberg state of the 1s exciton, which I didn't show. And from there, I can know the band gap minus the energy. So I measure the binding energy directly. Yeah. Okay. So can we realize exciton condensate? So one idea is that you just keep pumping the system and create a higher and higher density of exciton. But something more interesting happens. So here I'm shining the laser over here, and the dashed line shows the boundary of my sample. You can see that not only I create interlayer exciton over here, but also outside of my laser excitation. This makes sense because interlayer exciton can have long lifetime, so even though you generate it locally, it can diffuse to a different region. If I increase the pumping power, the diffusion with length becomes larger, and I see other area lights up as well. Compared with intralayer exciton, I see no diffusion at all. So initially, we may say that now if you generate exciton, they like to escape, so maybe this is not good for condensate. But on the other hand, because they diffuse, they can cool down, right? So you inevitably create laser heating under your laser spot, but as they move away from your laser excitation, they can have more time to cool down and potentially get trapped in these natural traps to create a high density and cold excitons. So we think that this could be actually a good feature, and potentially we can look for exciton condensate in these cold traps. Of course, we don't know exact nature of these cold traps now. We had some ideas, but we don't know for sure. These traps may be good for realizing condensate. So one thing we did is to look at the exciton density inside the trap and compare it with directly under the laser illumination. We find that inside the trap is actually not significantly lower. So that's another good thing. Because you have these natural traps, you can actually get pretty high density of excitons inside these traps. We find that the quantum degeneracy temperature is around 3 Kelvin. So it's still below our system temperature, but potentially we can realize much higher densities by designing traps or designing some mechanism we can shuffle excitons to these traps. Okay. So we are still trying to explore the optical detection of this exciton condensate, but meanwhile, this type of device structure gave us to, yeah.
Can you use strain to trap?
Yeah, that's a good question. So I think you can definitely use strain to trap. We don't have a good way to apply strain. So if you have some ideas, we can certainly discuss. Yeah. I know your work, like you use strain to confine excitons, right? So yeah, that's very interesting. Yeah. This also actually gives us electrical access, right? Because I have 2 layers separated by HBN, so you can imagine that I can create an individual contact to these layers and do a transport measurements. We haven't do the full-blown transport measurement yet, but one thing we can do is to apply a current in one layer and look at how the exciton moves together. So this will be probing the correlation between electron in one layer and the hole in the other layer. So ideally, if I apply electric field, I should see the exciton moves in the opposite direction if I apply on the electron layer. So this is exactly what we see by comparing the spatial distribution of excitons under certain electric field and without electric field. We can see that they actually move in response to the electric field. And you can also think about doing interesting valley physics, right? So they can have different Berry curvatures. I'm not going to discuss too much, but we are quite excited about this opportunity of combining electrical control with optical probe in this type of devices. So with that said, these were all done in the kind of a relatively simple system without any Maury potential. So now I'm going to discuss the work mainly spearheaded by Mohammad's group of probing these correlated electron and exciton inside a Maury system. Okay, so as Ajit has mentioned, you can create these Maury structures to trap both electrons and excitons. In our experiments, we are going to just focus on this particular material system, tungsten diselenide and tungsten disulfide, but in principle, you can do this with many different material combinations. These forms are actually a quite exciting platform to study fermionic and bosonic physics in a Hubbard model. The idea is that I can put electrons on this locally trapping potential, but I can also put excitons inside them. And I can control the density of the electrons and excitons independently, right? So I can apply the voltage to tune the carrier density, and I can change the pumping power to tune the exciton density. So in a simple regime where I have an empty lattice, you can create an exciton like this. But if I put 1 electron per Maury unit cell, the next time I create another exciton, this exciton will correspond to a doubly occupied electron set. So by comparing the energy between this exciton species, X1, and this exciton species we call X2, you can sort of have a feeling of what's the interaction between these two electrons, so you can sort of measure the interactions between the two, the on-site Coulomb potential. This is the rough idea. Another interesting regime is in an empty lattice. Now, if I pump the system really hard, I put a lot of excitons, let's say 1 exciton per Marie unit cell, and if now I add additional Marie exciton, another exciton, this exciton will be correspond to the doubly occupied electron side and doubly occupied hole side. So you can probe another type of interaction correspond to exciton-exciton correlation on the same lattice site. So this is a very versatile platform that allows us to do this type of measurements. Okay, so in the experiments, what we did is to exactly probe this kind of structures, and I want to mention that this similar phenomenon was observed by Chen Haojin's group here at UC Santa Barbara, and also Sufei Shi's group. Here I'm looking at a low pumping power regime. So relatively speaking, I'm putting fewer excitons compared with electrons. When I go to this half feeding state, suddenly there is a jump in the exciton energy correspond to the transition between this empty site exciton X1 and this doubly occupied exciton X2. If I increase the pumping power, I create more excitons that's occupying this lattice site. Then it would take fewer and fewer electrons to reach this single occupancy for the Marie lattice. So you see that the threshold for reaching this X2 transition becomes smaller and smaller, and also the gap size is different because eventually you will correspond to exciton-exciton correlation rather than electron-electron correlation as a pump very high. I didn't show it here, but we can actually, even under zero doping, we can completely fill the system with excitons, so looking at pure exciton interaction. And from this X2 feature, we speculate that we form an exciton correlated state where the exciton transport is suppressed. Then we developed another technique to directly probe the exciton transport, which is look at the exciton diffusion. So here I'm looking at the exciton diffusion in both real space along this axis and also energy resolve them so that I can only look at the X1 without looking at the more complicated X2. So this is just looking at this exciton diffusion in the simpler regime. If I compare this low power and high power regime, you see something quite striking, right? So in the low power regime, you see that X1 is more spread out, but high power regime, the X1 is actually more confined. So this is in stark difference from what I showed earlier for the Marie free system. There, when you pump the system, the exciton diffuse further away because of the repulsion. Here, initially it's spread out, but as you increase the pumping power, they actually become localized. So the diffusion length actually gets reduced. We attribute this to the formation of correlated states, exciton mod states, because we assume that that's when you reach 1 exciton per Marie unit cell. That's when the diffusion of exciton got suppressed. Okay. So this is in the diffusion in the high density regime where we create a lot of excitons. It turns out that we can also look at the dilute limit, right? So we can create a small number of excitons and look at how the electron filling influence the diffusion of the excitons. So this is one example where we use a very small laser power around 1 nanowatt per micrometers and look at the diffusion of the exciton. And we vary the density of the electron inside the system. So on the horizontal axis, I'm showing the filling factor as a function of gate voltage, and this is the diffusion length. So quite strikingly, initially in this empty lattice, the diffusion is small, but when we approach this electronic multi-insulator, there is a quite strong enhancement of the diffusion. This was quite counterintuitive initially for us because we would expect in the electronic insulating state, the exciton diffusion should also be impeded. You may ask, maybe this is due to the lifetime of the exciton that's changing with gate voltage. So we also measure the lifetime, and we found that the lifetime actually decreases. So we plot this parameter that's related to diffusivity, which is the diffusion length squared divided by the lifetime. And related to diffusivity, we find that exciton diffusivity is actually enhanced by almost 2 orders of magnitude at the Mott transition, at this electronic Mott transition. So this was a really very surprising for us. And Mohammed and Michael Knapp, they came up with this really, I think, a very elegant idea to explain this phenomena. In the neutral exciton, neutral charge regime, the exciton diffuse as a collective particle, right? We call this monogamous diffusion, so the electron hole move together. But when you fill the Mott insulator state, there is one electron per lattice site. Here, because what Ajit talks about is an intercell Maury exciton, so the location of the electron is actually slightly mismatched from the location of the holes. So you form an exciton like this. It has a slight mismatch in the real space. What makes this interesting is that here now I don't need the whole exciton to diffuse. Actually, the high exciton as a collective particle don't want to diffuse because it will double occupy this site, but only holes needs to turn on in order for the emission to be diffused to a different region. So you have a reduction in the effective mass, right? So you just have a half of the particle to diffuse. And also because I have electrons here, it makes the hole more likely to go into this intermediate state. In other words, reduce the effective potential because the electron is right in the middle between these two hole barriers. So you have two effects that helps to reduce promote the diffusion of excitons in such a system. And once you overdope the system above mu equals 1, you recover the initial state, but now you have a multi-exciton diffusion, so where two electrons are on the same lattice site. So this was actually provide a quite intuitive picture of why we see this dramatic enhancement diffusion at this particular region. Yes?
So how do you reconcile this observation with the observation a few slides ago that the diffusion is suppressed?
Oh, so that's a great question. So in that experiment, we are using a very high pumping power. So we are feeding the excitons, almost 1 exciton per Maury unit cell. Here, the key observation was actually, we didn't intentionally try to do this. We were very interested in the low power regime. So we go to the low power regime where there is very few exciton in the Maury cell. So it's mainly the electron interacting with the exciton. Yeah.
Could you show the lifetime?
Oh, yeah. So this is the lifetime.
So the lifetime really is much shorter at above mu equals 1, right?
Yeah.
So is this due to the fact that excitons now are spatially better overlapping in the transverse direction?
I see.
Because the same argument you make for the reduced barrier for electrons, also for the additional electrons will see as a weaker potential.
Yeah, that's excellent. Yeah, I think so. Yeah, we didn't think about it, but that's a very good suggestion. Yeah, actually, we didn't understand this. Okay. But this, I think, it opens up very interesting regime because now we can not only probe exciton, right? Because the valley spin valley coupling, we can actually also potentially probe how spin diffusion happens in this system and how it's modified, for example, by the underlying magnetic structures of electrons in the Maury systems. Okay, so we are quite excited about this work. So in the last part of work, I will try to describe some of the collaborative efforts with Mohammed's group, trying to develop sub-wavelength control of excitons. So in this workshop, we have seen a series of wonderful talks of using light to induce different phase transitions in these various quantum materials. So one idea we had is that typically these are done with just free space. What happens if we pattern this light intensity spatially, right? So what happens if we spatially modulate the light intensity? Can we do something similar to the atoms community where they can use this to impose optical lattice and confine atoms? And actually, indeed, there was this theoretical work from Mohammed's group of using this spatially patterned field to create some flat band in graphene structures. This adds some advantages because now you can dynamically modulate this periodic potential and look for example, phase separations. So not only for 2D materials, but also perhaps very interesting for other quantum materials. Of course, one of the challenges is that for atoms, we can just interfere two free space beams. The periodicity can be pretty large, comparable to the wavelengths. Here, for solid-state system, we want this periodicity to be quite small, to be below the diffraction limit, similar to a Maury, right? So where we can see a strong effect. To overcome this challenge, we borrowed some ideas from my colleague Alex Hai in Hong Kong, who used to work with Hong Kong Park and Misha Lukin, so like 10 years ago. They developed this technique of creating very good surface plasma polaritons with very interesting properties. So let me explain what it is. So you are looking at some crystal, single crystalline silver, and we just etch a bunch of trenches, so just a bunch of gratings into this single crystalline silver. And what I can do is to pump the system from this in-coupling structure, and the surface plasma polariton gets excited, and they will propagate along these gratings, and will be diffracted from this out-coupling structure. I emphasize single crystalline silver because one of the issues with plasmonic structure is that they typically have high loss. Here you can have low loss because of this absence of boundaries. And also, this type of structure allows you to realize very interesting dispersionless propagation. So this is very similar to what Vinod did for these hyperbolic materials, and also Dmitry Basov talked about in these natural polaritons. Because these are highly anisotropic along this direction versus this direction, right? So the property is very different. Along this direction, you are just seeing the gratings. Along this direction, you see air and the air grating repeating itself. So you form this periodic structure, alternating structure. So you can engineer a hyperbolic dispersion that's dependent on the wavelength. When the wavelength is small, you can have this hyperbolic dispersion, and when the wavelength is large, it turns to this normal elliptical dispersion. And there is this transition frequency where it's flat, the dispersion is flat. So this means that all of the group velocity will be pointing upwards. So this is the simulation where we show that in the elliptical and the hyperbolic and elliptical region, the beam would diverge. But in this dispersionless region, the beam will propagate along a single groove. So this is actually just a single groove, and it is concentrated on this single groove. So at this particular wavelength, you can deliver plasmonic power very efficiently because it doesn't disperse into other gratings. So it's confined only on a single grating. And this allows us to also potentially control individual gratings, right? So I can potentially vary the intensity only on this grating and not on the other grating. Okay. So in the experiment, what we did is then to place a TMD right on top of this plasmonic structure. So I excite the system over here, and the surface plasma propagates and impose some spatially varying optical field on the 2D material. If I look at the simulation, so this is a cross-section taking a cut like over here, and the electric field is actually very tightly confined to the corners of the ridges. So even the ridge is 100 nanometer, the optic field is around 10 nanometer because of this antenna effect. And how does this affect the excitons? Right, so actually we use this quite well-established now idea of using AC start shift. If you drive the system just below the exciton transition, you induce AC shift, that start shift, that blue shift your exciton, and it's proportional to the intensity of your laser. So here, if I look at the cross-section, the intensity is maximum at the edge at these two bunny ears, and it's minimum in the gap and in the middle. So this creates an AC start shift where you have high energy right over here, but low energy over these three spots. So, okay. I'll wrap up soon. Okay. So when we do the experiments, we first compare a free space like AC start shift by pumping and probing at the same spot. You see that typical AC start shift. And then we do the experiment where we pump remotely and launch the exciton from the incoupler and launch the surface plasma polaritons from the incoupler and create some modulation on these TMD layers and probe in the far field. We see similar shift, but if you look at the power required to induce the similar AC stack shift, you see that we actually have a drastic reduction in the amount of power that's needed. This is because the light field is so much confined into a very tiny space around nanometers, so now I don't need very strong power to induce the same amount of shift. So it provides a quite powerful, power-efficient scheme to induce interesting photon-induced physics. And also because we are pumping and probing at the different regions, so this allows us to do different things of pump rejection. This makes the measurement also a bit simpler. One thing we notice is that in addition to the shift of the neutral exciton energy, there is actually also significant broadening when we pump the system with surface plasma polaritons. So you see that there is broadening for this SPP pumped case, but no broadening for this conventional case. This is due to the lattice effect, right? Because we have a lattice, different regions, we have different amount of shift. So if you average them out, you would broaden the bandwidth. Okay, so we are still trying to see if we see any evidence for this periodic modulation. And for example, we think about maybe how this could modify the exciton dynamics in such optical lattice, and how can it modify the thermalization of exciton lattice. So there are still very interesting direction to go, but this is something that we have achieved so far. Okay, so I think I'll wrap up. I think that hopefully I've shown you that these 2D materials, they provide a very interesting platform, for example, to look at the correlated electronic states. On the other hand, you can integrate them with surface plasma polaritons to impose a sub-wavelength probe and also potentially control their properties. For example, maybe the polaritons that Dmitry Basov talked about, maybe you can use those natural polaritons to do similar physics. And eventually, if you combine these two systems, you can develop a very nice way to probe the physics at deep sub-wavelength scale and also potentially control them at sub-wavelength scale. So, for example, maybe combining bilayers with this type of structure. So we are very excited about these potential new opportunities. So I will conclude here, and thank you again for your attention. Thank you so much.
Thank you, Zhou, for the very interesting talk.
Yeah, I'm curious, do you ever see a delay between, in just the last piece of physics you observed?
Yeah.
Because you're pumping at one location and probing at another location? Yeah.
So in principle, you should see a delay. We didn't compare the time between the pump and this probe. What we did is to directly see where does this change happen. So we didn't do a very systematic look at the difference between the pump and probe pulse. So we didn't calibrate that.
So what's the time scale, the delta t?
Delta t is femtosecond. So this is the pulse width. So essentially you have a pulse and you arrive here at some period of time, and we just look at this period of time. Okay. So we didn't calibrate it
thank you.
Carefully.
Any other questions?
Very beautiful picture about the fast diffusion of excitons. So in that case, I wonder, do you actually have a charge current because your electron is not moving?
Right. So if you have a charge current, it will be still isotropic. So I don't know if it creates a net current, right? So because the hole is moving along all different directions.
Yeah, for sure. But then just imagining if I can inject, let's say, exciton from one side. So essentially, this will be a
exactly.
Perfect.
This would be very interesting. So, for example, maybe I can apply the electric field and make it polar.
Yeah, so the actually transfer.
Fast, or maybe look at the edge of the sample.
Okay, cool. Can I ask a second? Okay. So second question is, do you have a quantitative way of understanding how the Wigner crystal screening causes the exciton to change? What is the dielectric function, for example? What's the frequency that matters most?
Yeah, so short answer is that I don't know if you guys, anyone of you know like how to describe the dielectric function. Let's chat.
Okay,
yeah,
thank you.
we only have like a very hand-wavy description. Yeah.
Thank you.
Okay, one last question.
Might be a naive, non-exciton expert question, but is there a way to, can you probe these plasmon polaritons excitons that would, for ordinary light, be dark? So they, because they're either momentum mismatched or polarization mismatched.
Yeah. So this is actually something we put into our proposal. Yeah. So like you can see here, in the near field, this guy is really tightly confined. Yeah. So if you do Fourier Fourier transfer, this corresponds to very large momentum. Okay. And we are very interested in the momentum dark states. So people have looked at spin dark state, but not a momentum state. This could potentially enable study of momentum dark state. Yeah.
Great. Okay, so let's thank you again.
Thank you.